Alright, good morning. Today we're going to be looking at some problems with Newton's laws. The first thing that we need to look at is weight. Weight is a force, and since weight is a force, we can create a formula for it. Weight is the force of gravity on an object. So it's pulling that object towards the center of the earth. And since it's a force, we can say weight is equal to mass times acceleration. Just like we can say force equals mass times acceleration. Except in this case, weight would be equal to a specific acceleration. It would be the acceleration due to gravity. So sometimes we'll just say mass times the acceleration due to gravity, which is 9.8 meters per second squared. Sometimes we round it to 10 meters per second squared. Alright, so let's look at some problems involving weight. Here we have a history book that weighs 40 newtons. It is placed on top of a literature book that weighs 10 newtons. If up is considered the positive direction, what is the force that the history book exerts on the literature book? Okay, so we've got the history book placed on top of the literature book. Okay. And you know from these things, from the previous exercise on free body diagrams, how to create free body diagrams. So let's look at that history book. The force of gravity is pulling it down, and then the force from the literature book is pushing it up. And then if we start looking at the literature book down here, so I'm going to redraw it down here, we've got the force of gravity pulling it down its weight, but we also have the force of the history book pushing down it. So I'll just say force of the history book here. And then we have the force of the table pushing this up, what we call the normal force in this case. Okay? And up here, that would also be the normal force, except the thing creating the normal force would be the literature book. Alright, so now, let's look at doing the force of the history book and what it exerts on the literature book. Well, it would just be the weight of the history book here. This is what's exerting a force on the literature book. So let's do the weight of the literature book is equal to mass times acceleration due to gravity. You'd also write out the word weight instead of force. Do mass times acceleration due to gravity. Sorry, sometimes my pen makes these straight lines. Let's take a look at plugging in some numbers to this. Okay, so we know that the history book weighs 40 newtons. So we don't really need to do the calculations. We just already know that the weight of the history book is going to be 40 newtons. And since we know that weight, it is in a downward direction, we would just say that it is pushing down on that literature book with negative 40 newtons of force. Now, the literature book also exerts a force on the history book. Well, that force has to be equal and opposite it, so it would end up being a positive 40 newtons. And we know this because the positive direction is up and it's defined in our problem. So this would have to be positive, this would have to be negative. All right, let's look at the next problem. Problem number 3. An object with a mass of 9 kilograms is accelerated at 5 meters per second squared. What is the net force acting on the object? So we're just going to use the formula force equals mass times acceleration and plug in numbers to figure out the net force here. Okay, so we've got net force is equal to the mass, 9 kilograms, times the acceleration, 5 meters per second squared, and we get the net force is equal to 45 newtons. And that's a fairly simple problem. So then let's go on to another one. Problem number 5. A net force of 80 newtons is required to accelerate an object at 8 meters per second squared. What force is required to accelerate the same object at 2 meters per second squared? Okay. So once again, we're just going to be using Newton's second law. Force equals mass times acceleration. I'm going to get rid of the sigma in front just to have it so it's a little bit more simple on this one. Let's see here. We've got mass, the first mass, and the first acceleration, and the first force that we're going to put on it. Alright, and then we start pushing that thing again with another force. It's the same mass, so I'm just going to put m1 again, and then it's going to have another acceleration. So let's solve for the mass here, and we get the mass would be equal to, let's divide out the acceleration, the force over the acceleration, the first force over the first acceleration. We can do the same thing over here, and this time we would get the same mass is equal to the second force times the second acceleration. So since the masses are constant, we can set these two equations equal to each other. Okay. We know what the first force is. It's 80 newtons. It's given to us in the problem. We know what the first acceleration is, 8 meters per second squared. We know what the second acceleration is, 2 meters per second squared. So we know this one, and this one. That means we can solve for this. So I'm going to rearrange that equation to do that. So it's multiply this side by the second acceleration, and multiply this side by the second acceleration. So then when we get that second force is equal to the first force times the second acceleration divided by the first acceleration. So let's plug in some numbers now. 80 newtons was the first force. The second acceleration was 2 meters per second squared. And the first acceleration was 8 meters per second squared. So that would give us 160 over 8. And if we do 160 over 8, we would end up with 20 newtons of force. So our second, if you were to push that thing with 20 newtons of force, it would only accelerate at 2 meters per second squared. Alright. So let's look at number 7 now. While reading number 7, you can see that we're going to have to do a free body diagram. So let's read through it. It says a 2-kilogram box that rests on a frictionless horizontal surface has 3 forces acting upon it. A 3 Newton force to the left, a 10 Newton force to the right, and a 4 Newton force to the left. What is the box's acceleration? Okay. Now, the very first thing when you get these things is draw your free body diagram. So we have a 3 Newton force to the left, a 10 Newton force to the right, and a 4 Newton force to the left. So let's do that here. Alright, now we've got to set up a formula for these things here. Okay. We need to know that the sum of all the forces is equal to the mass times the acceleration. So the next thing that we're going to do is look at the sum of the forces here. So we've got to add up all the forces acting on this box, add and subtract them. So it says that we need to let the positive direction be to the right. So we know that to the right is positive is defined for us in this problem. Right, so that means that the 4 and the 3 end up being negative. So if we have -4, -3, that's really like -7 newtons of force to the left, okay, on this box, and 10 newtons of positive force to the right. 10 minus 7 would give us a net force, or the sum of the forces either way, of 3 newtons. Okay, so we know that this number will be 3 newtons. Now we've got to solve for acceleration, so let me rearrange this equation to solve for acceleration. We divide out mass on both sides, we get left with acceleration. So acceleration is equal to the sum of the forces, or the net force on the object, divided by the mass of the object. And we figured out the sum of the forces, the net forces, to be 3 newtons, and it told us that the mass of the box is 2 kilograms, so let's plug in 2 kilograms here, and 3 divided by 2 would give us 1.5, and its acceleration meters per second squared. And let me show you how we end up with those units. The newton right there, so let's see, the newton is really equal to, 1 newton is equal to 1 kilogram times 1 meter per second squared, and that just comes from your equation force equals mass times acceleration. Right, so if we use this for newtons, okay, if we said that we had 3 kilograms times meters per second squared instead of saying we had 3 newtons, and then we had 2 kilograms on the bottom, you would see the kilograms canceling out here, leaving us with just meters per second squared for our units. Alright, now let's look at number 9. Number 9 says a 10 kilogram object in space is acted upon by exactly 2 forces, a 10 Newton force and a 60 Newton force. It doesn't give us the directions here, so we need to read a little bit further to try and figure out some more information. What is the greatest acceleration that the object could have? And that's what A says, and B says what's the least acceleration that could have? Well, the greatest acceleration it could have is when those forces are in the same direction, and the least acceleration it could have is when those forces would be in opposite directions. So I'm drawing their free body diagram. Same direction, those forces would be pointing the same way, and if they're least acceleration, they would have to be pointing in opposite ways. So here we'd have 10 and 60, and here we could have 10 and 60. All right? So if they're in the same direction, we would add them up, and we would see that the net force on the object would be 70 newtons here. Over here, we'd have to subtract them, and we'd see that the net force on the object would actually be 50 newtons. All right. Now let's go back to a second law. Force equals mass times acceleration, or net force equals mass times acceleration. Well, we know what the mass of the object is. It's 10. So if we wanted to solve for acceleration, we can look back at the previous problem, and we had that formula for acceleration right here. We solved for it. It's equal to the net force divided by the mass. So again, divide out the mass. We get acceleration is equal to the net force, or the sum of all the forces, divided by the mass. So in this case, in A, we would want to take 70 newtons and divide it by 10 kilograms, and that would give us 7 meters per second squared as our greatest acceleration. Now over here, we would want to take 50 newtons divided by 10 kilograms, and we get 5 meters per second squared as our least amount of acceleration. Alright, and then comes number 11, and we're just going to have you cross out number 11 for now. Now this is the end of part 1. I'm going to do 13 and 15 in a part 2. So look for part 2. This is it for part 1.